extra strong Roman concrete,
fully hydraulic,
structural molded connections.
It's the
structural
Engineering podcast.
Hey, welcome to this week's episode of the Structural Engineering Podcast. My name's Max,
And I'm Zach.
and we're going to talk about the R value.
Yes. This week we're going to dive, I'd say, to a pretty good level of like deciding on your R value, your response modification factor for
We're diving
seismic
into the
systems.
shallow end of the pool.
Correct.
Yes. We're not going 8 feet.
No. 6 inches.
6 inches.
So Max, what do you got for us this week?
Let's start with the news article.
Okay.
This one is not groundbreaking, but it was pretty cool. I kind of like looking at this bridge infrastructure stuff. This is something that popped up on the ENR website, Engineering News Record. It is titled, Chicago's Lakeshore Drive Bridge Closes for Emergency Repairs. So this was a fracture to a girder beam, I think at the approach ramp, actually, a 33-year-old structure to a 260 about foot bridge.
Wow.
Yeah.
Can I take a guess? I haven't read the article.
Oh, really?
Yeah. I just forwarded it to you.
You
I
might
saw
like
the
this.
It's not very old.
It's not very old.
Although
It does have a bad sufficiency rating. I think they gave it a 5 out of 9.
Okay.
For
Is
substructure.
there any chance this is due to the recent weather?
That's pretty good.
Really?
That's what it is.
Huh.
Yeah.
Okay.
Yeah,
I'm not lying. I didn't read
No,
it.
that was yeah.
Okay,
You're right on. So this is most likely due to the mega temperature swings they had a little bit ago. They said something like negative 20 to 40 degrees temperature swing in a day, which will just crack the heck out of your steel, I guess.
Talking about some expansion.
Yeah, really.
I wonder what sort of in bridges. There's obviously it's out in the it's outside, so it's dealing with those big temperature swings. I know they design bearing plates and stuff so that there's movement. And I wonder, there's a bridge that had some localized failures, didn't collapse, that actually one of the ends that was supposed to be a roller actually seized up.
Yeah, that's a really common thing that happens. I should not go too far into this because now I'll just talk forever.
Yeah.
There is some equipment. People were trying to test the frequency of bridges, like to see when they could be failing, but they realized like if you put a vibration sensor on a bridge, if it was sort of breaking down, you'd expect it to get looser, but different things happen at different times, and like bearing plates will get stiffer, or these roller bearings will kind of start to seize, so the bridge might actually get stiffer over time. At the same time it deteriorates, and you might not see, basically you don't get any good information. So yes, these roller bearings totally seize up.
Seems like a bad plan.
Yeah.
Have a roller bearing that's not well maintained. I know that's the largest, like the biggest issue with the United States infrastructure is we don't maintain it.
Yeah, we don't.
For some reason, we believe it's better to spend $10 billion in 30 years rather than, let's say, $1 million a year to maintain it.
Yeah, there's all sorts of reasons for that, and it doesn't make any sense. The other thing I'll say about these is, as far as the roller bearings go, expansion joints in bridges are one of the most likely things to go, the hardest things to maintain. So I know currently bridges, the trajectory is to design without expansion joints if you can. So just put those stresses into the bridge. Obviously, there can be a lot of stress, but if you don't have a hinge in your bridge, that's even better.
Is that I would think that would be easier
concrete
done with concrete.
Yeah, so absolutely.
That's interesting. Well, we'll in the tech notes have this picture.
Yeah, it's a pretty cool picture. I mean, it's a big crack, and they, I think it's a double-decker bridge, but the article said a brace is holding it up currently that can hold 1 million pounds.
The shoring system?
Yeah, the shoring system is a 1 million pound brace. It looked pretty intense. It's still open. The bridge is operational. They're just gonna throw some plates over. Like the same kind of repair I've done on deteriorated webs. They're just going to plate both sides and carry on.
Now, would you? I don't know if the article went into this, but would you anticipate any litigation?
I don't think so. I mean, it's out of the statute of limitations, I believe. I mean, the
Do you think this will change bridge design moving forward?
no.
Other question: is the picture just the angle, or is the bridge blue? Is it blue or rusty? Is it exposed steel?
It might just be like gray.
Okay.
Yeah.
Well,
with that,
you guys listening, jump into the notes.
Is
And
it a blue
you
dress
let us
or a
know
gray
what you think.
dress?
Exactly. What
Yeah.
color is the dress or the bridge curtain? I kind of like the idea of thinking this bridge is blue.
Yeah,
But
I
when
thought
you look
looking at the picture
pictures-
that it hadn't gotten knocked off its pier, but that's not what happened.
Yeah.
All right, yeah, check it out. It's kind of a fun little article. They're definitely using it as some leverage to get more funding for bridges, which they should. So that's hopefully something that will come out of it that's pretty good.
The other thing that seems very interesting is they have, these concrete column buttresses.
Yeah.
But then they have steel girders on the bridge. I would think a lot of times you see those double I shapes or built up concrete shape. I wonder why they went with steel. Must have been at the time the best solution.
Yeah, we see concrete around here because box girders and concrete double T sort of stuff around here is actually cheaper than steel for bridges.
Yeah.
But that's because we have a lot of concrete.
Here in Colorado.
Here in Colorado. Yeah, so with that,
Don't go on any steel bridges.
don't go on any steel bridges and I check for cracks. Anyway,
Always check your bridge before you
check
drive
your bridge
over
before you drive over it. Let's talk about R's.
it. Ours.
What?
What is an R to you,
What's an
Max? What does R make you feel like?
It makes me feel.
So before Max is very philosophical here, what we're talking about is seismic design of a structure.
The response coefficient factor, which we discussed a little while ago, is sort of a combination of the damping ratio and what was the other
Ductility.
Ductility and the
That's
ductility.
built into that system. Why do we care about that?
It is directly, or rather inversely, proportional to the force when we're looking at the equivalent lateral force method, the ELF method, that the building sees. So
Where does this ELF method come from, Max?
it comes from
Talking about ELF, so are we talking about Santa over here?
the minimum design loads for buildings and other structures, otherwise known as ASC 710.
Or 16 or 5?
Well, sometimes. Depends which one you're holding.
We've got
Yeah, it's the most basic go-to lateral force method. I mean, it seems like 95% of your cases, I've never done anything different. You're looking at the equivalent lateral force method for seismic design. And the equation for this, so to take your lateral loads and put it into the building, you have your SDS factor, importance factor, and you're dividing this by your R value, and then multiplying that CS by your weight of the building. So since you're dividing by your R, the higher your R can be, the lower the force that you have to transfer as a lateral force due to seismicity will be.
Right. And your SDS is your earthquake spectral response acceleration parameter at a short period. And that is all based off of your seismicity of where you're at. And that comes in S sub 1 and S sub 2, or S sub S values, and then off of your site conditions for your soil.
Mm-hmm. Yeah, soil plays a big role here.
Huge role. And then that you kind of determine those factors in chapter 11 of ASC 7, and then going into the design of your building structure into 12, and that's where, where you're going with the ELF method and getting your lateral load.
Yeah. So kind of how this came up, I think, is we were talking in the office a little while ago about using an R of a 3 or a 3.25. And conveniently, there was a modern steel article that said the exact same thing, basically arguing for a 3.25 R value in steel.
Right. And I think a big thing before we really dive into these different systems is what's driving these. And I think we'll see while talking through this that not only is it money, but it's also based off of in your region. Do you have steel companies that have experience with this? Do you have subs that have experience? Do you have contractors with experience? Maybe using a high, let's say we're even going up to a higher system.
So you're doing an eccentrically brace frame.
Right, in Colorado. I wouldn't think that's used a lot. And so once you send that out, those steel subs are going to be kind of confused, maybe not full, experienced with removing backing bars and then AWS, the welding code of D1.8, which goes into seismic stuff. So I think, money drives it just on a basis of steel weight and concrete for your foundations, but also what you have readily available in knowledge at your steel fabricators, and then I think that's those things. So,
well, there's the money side, and then there's the building performance, the ductility.
That's what I was gonna say. Yeah, that was the last thing, is building performance.
Yeah. There's some argument that a higher R value, something like a 3.25, which would be an ordinary brace frame, provides more ductility to the building. But maybe let's say, before we even talk about that, what's the spectrum of R values here? When we're looking at steel and we're saying an R of 3, this is a steel building not specifically designed for seismic.
Right.
So that is just any old brace. You design to the loads, no special considerations here. You want a moment frame, go to town.
Right, you design for those loads.
Yep.
There's no extra restrictions. If you want to weld it, you just weld it.
Yep.
If you want to, whatever you want to do, you kind of more or less just do.
Party on.
Party on, Garth. Yeah, so that's our low end is the R of 3. Our high end is an R of 8, and that could be something like an eccentric brace frame or a BRB, a buckling restrained brace frame. And those are kind of the two. Oh, I guess also you have your moment frames. So a special moment frame also is an R of 8, or a special reinforced concrete.
Jumping from that 3 to 3 1/4 is just going from the steel system not specifically designed to a steel ordinary concentrically braced frame. So basically just hitting your first parameters for ductility requirements. So as far as detailing goes, you're just getting into some lighter requirements for ductility. You have a slightly lower load that ends up getting to this frame. And I actually don't know, but we've got the book here. What's the overstrength factor difference? What is the omega you've got? So we've got here a 3 1/4
and a 3
versus a 3.
So 3 1/4 for a steel ordinary concentric, and then 3 for an R of 3 system.
So it might be a wash, because you actually get slightly lower loads, but then your overstrength is a little bit higher.
Right.
So that probably comes out to be the same.
For what?
As far as your collectors and stuff, items that need overstrength.
Right.
Yeah.
Okay, so now you're in ASC 7. You've picked. You're kind of trying to pick your R value. You understand what that is. You understand the kind of ductility. At what point do you decide I'm gonna do something greater than 3? I think for the majority of the time, you're just going to hit 3 and call it good.
Call it good, yeah. Us being in Colorado, out on the plains at least, very low seismicity. And we'll say we can only use an R of 3 in A, B, and C seismic regions, which for us basically don't see anything else.
Right, covers everything here in Colorado. We see
Colorado.
stuff beyond outside of the state, but
an R of 3 is probably adequate. So what was the argument of this article, basically? What would push you to use a 3 1/4?
Really, it just drives you into ductility stuff.
Yep.
So the major, if you want to think about it, your R of 3 system is just that really strong kind of buff person. Buff system. So your braces are going to be bigger. And it's just like all out of just brute
force. The article that we were looking at, compared these two systems designed to the same load, I assume. One not detailed for seismicity.
Yeah.
It used 8x8 HSS tubes.
Right.
Right. Big burly tubes. And then the second system they tested was ordinary concentric brace frame, right? And basically had 6x6 tubes.
Correct. Because you have to be moderately ductile for your brace elements, and that's your width, the thickness has to be within a certain range, and so that's where it drives you to using a different tube size.
And what they found, now these were different orientations, but the 8x8 tube at a very low story drift, 0.3%, buckled, what's the word? Not good. Catastrophically. It buckled catastrophically. The thing that this brace has, though, is something they define as reserve capacity, which they specifically said, this is not ductility. Reserve capacity should be seen as a complementary to ductility. And I see the reserve capacity in this frame as being basically the larger gusset plates being required and the larger connections almost acting as a bit of a moment frame. So although it lost almost all of its strength when this brace buckled, it still had some ability to resist lateral forces.
Right. Yeah. And then when they did the eccentric, or the ordinary concentric brace frames, they found that it did go into that kind of second limit state of creating a plastic hinge. It didn't buckle the thing. It went to a way higher story drift before failure.
1.5% story drift, right?
Right. So significantly more than...
With no sign of failure, they say at 1.5 story drift.
Right.
And the elasticity, the ductility in this system is basically, there's yielding of the braces a little bit, but it's also of the gusset plates. So there's some specific detailing to those gusset plates that they will yield, dissipate energy without total failure.
Right. Okay. So now you're the design professional on this project. How do you go forward determining which one you want to use?
I don't know. I think it would be definitely a little bit looking at what the building's purpose is in life. Not just like the occupancy category, but a little bit the occupancy category, right? If this is something that you think should have a little bit more resilience and maybe have the discussion with the owner and they agree, you have a slightly more expensive system with something greater than an RF3. There's some argument that you can actually save some money. Basically, you reduce your forces by 8%. Is the foundation costly enough that 8% less of it at the lateral system is going to save you a bunch of money? Probably not. I don't know. What do you think? Like as far as like directing that.
I don't think in my opinion, the research I've done, I don't think going to an RF 3.25 does pretty much anything with your costs. If anything, it probably increases a little bit in some areas.
Yes,
is what I've seen. And so like, if you're just going off the code, just RF 3 every time.
Yeah, I think so. If it was someplace with low seismicity, A or B, just an office building, let's say, I would probably just default to 3 almost always.
Right, and I think when you're going to start seeing in this low seismic area, to maybe there's some moderate seismicity in Colorado, you're really not going to see a savings until you get up to those systems of an RF6, maybe an RF4, but an RF8, and that's where you're going to start seeing multi-story buildings that's maybe cladded in brick, super heavy buildings.
Yeah.
Where in the long direction they're going to be driven by seismic, and you're going to see a massive savings in your foundation system by going to a higher R value, and that's something I think you for like a design build project you could figure out pretty easily early on if you want to take that direction with your building. Now, a 1 to 2 story building using a BRB system in Colorado is probably not. We're going to find very a lot of economy, but it's such a hard decision to make in a blanket statement because every building's different.
Yep.
Maybe some buildings you can put in a brace, you can brace the heck out of it, and then you're not trying to do anything crazy. We know in reality the architect wants one brace, maybe, in the whole building. And so now you're trying to shove these crazy loads through it. And, okay, sure, your braces one size, or okay, but that foundation system is going to be destroyed when using that lower R value. So I think a big thing in Colorado is when you start getting these taller buildings cladded in brick, and maybe as well, we have really bad poor soils out here, horrible soil, notoriously bad soils. So with a lot of clay. So when you're needing to have to stay to a bearing, let's say a pad footing or whatnot kind of system, that's where you're going to start seeing savings, is you're going to get those lower bearing pressures.
I could especially see if you have a minimum dead load requirement. Where we have swelling soils, you might have a high minimum dead load, and if you need a giant pad footing to account for your large lateral load, you might not even be meeting that minimum dead load. So that would be a great workaround. I think looking at higher R's is the strategy of go big or go home, where going from a 3 to a 3.25, you're adding a little complexity at the hope of saving, adding a little bit of ductility. But once you're getting there, maybe just go all the way. And something that's really nice about BRBs is if you're in an area that doesn't have a lot of high seismicity, a lot of manufacturers or steel fabricators rather might not have the experience to put together the eccentric brace frame or something. These more complicated details, and they'll upcharge for that complexity for them.
Right.
Well, you get a bolt-on BRB, you get a lot of advantages. The steel fabricator doesn't have to do anything special for them, more or less. So I don't know. I think you could see a lot of advantages from that.
Yeah, and in this article, they also discussed they went through a case study of a building. I want to say it's in Michigan. It's a moderately seismic region, and they found using an eccentric brace frame was actually a huge cost savings. And it was a high importance factor, multi-story building. One big driver too is they were driven by the architect to use tube columns, which in any sort of...
And this is a 3-story building?
3-story building, yeah. So in any sort of big, you could do an RF3 and try to develop your, maybe a moment frame or brace frame with these tube columns and whatnot, but they found that going to an eccentric brace frame, not only did they lower the loads, but they made the connections a lot better, because you don't have that. Now you have a link in the middle of your beam, and you're not doing too much at the end regions of your beam to your tube columns. And then they also wanted this big open look, so with that you got this link in the center, so they pull the braces back out a little bit. And so this was a huge case study to show like how beneficial it can be to use an RF8 system in a moderately seismic region. And again, this will be linked below. Definitely something really cool to look over. So to me, coming from a super high seismic region of the Northwest and then coming to Colorado where like RF3 is always thrown into everything, and I'm used to everything being special. I've never even used an RF3 system until I came to Colorado. I've never even like really heard about it. I think it's really cool that firms here are now looking to use these higher level systems, more ductility and stuff, to get structures in a moderate to low seismic region to work more efficiently. And I think it's super cool to see that happening, rather than just throwing an RF3 at everything. We've been through our research found, both in Colorado and then this one that's in Michigan and stuff, like engineers are starting to think a lot further through that whole story of, rather than like, just RF3 for everything. Sure, no, a 1-story building, RF3, it doesn't bother me, but you get a couple stories, and all of a sudden that seismic's driving a lot of things.
There is a weird conflicting, path here also, which is you start with an RF3 and maybe you say, wow, this building is actually seismically controlled in one direction. That's amazing. We're in Colorado, who thought? And then if you look at bumping up your R value, you may go down to a point where the building is no longer seismically controlled in that direction. So like as you're increasing that complexity in your system, you don't even need it anymore. So I could see that as sort of turning a lot of people away as far as like even dealing with something of a higher R value. Once you're past 3, in Colorado with a lot of wind might just take back over. But yeah, we are seeing definitely a change, which is pretty neat.
Absolutely. And that maybe that's where you go into Yeah, and so you have an RF3, an RF3 and a quarter for ordinary concentric, and then an RF6 for special concentric, and then RF8 for steel eccentrically braced frame. So there's a couple different steps you can take in there. But I totally agree with you. At some point, your wind will govern, especially as you go up the mountains and you're starting to see wind speeds of 180 miles an hour. Mm-hmm. Your seismic's going to be a lot smaller.
There was a quote in this article. I wonder if we can find it if I start to describe it here. And it really kind of sold me on not using RF3. And you remember what this one is basically relying on an untested reserve capacity idea. Let's see if we can track this thing down. The idea, more or less, is though that the reserve capacity of these RF3 braces is pretty much unknown. So once you get to a point where you buckle, now in this test, once it buckled, it was shown to have a high reserve capacity in this one instance, but that isn't always going to be the case.
Oh, so here it is. So it says even though the nature of this reserve capacity is not well understood and can vary widely, there's still some collapse prevention built into that. And it says that research to date has not thoroughly studied reserve capacity, so relying on it without proper understanding is moderate seismic region jeopardizes safety.
Yeah, that kind of sold me, I think. As soon as you get into any level of seismicity, not to touch RF3. It's just not tested for that reserve capacity system.
Right, so it's using engineering judgment at that point,
yep,
rather than a codified element.
Mm-hmm.
And I think that was a very good point.
Yeah.
And something that needs to be thought through a lot. So, so I would say to conclude it, there's really no straight answer. It's so dependent on your building system or your building, the layout of your building, where it's located. There's even, irregularities and stuff that you kind of have to consider with working through these different systems. So we'd love to hear from what you guys and understand kind of your experience and your, your opinion on these different systems. I would say, I don't want to speak for Max, but there's probably more practicality in moving up to a higher RF6, RF8 in Colorado with a heavier building, maybe trying to push your pressures. But there is something to be said and something to think through. And that's kind of the cool thing with talking about this is just having that thought of should I have a system with a little ductility versus a system like this that is really just based off of just pushing that reserve capacity that is hopefully there, right? So I think that's really the
which can
conclusion
vary
here.
widely, which is what it says.
Right.
So,
Right. Everyone's going to detail it differently. Everyone's going to design it a little differently. And so I think that's the take home is it's such a per basis thing, but just because you're in low to moderate, I'd say moderate is probably more of where this happens. You look at those higher systems for savings in your building, and if you get to a structure that that maybe it's an owner that wants to be a little bit more forward, a little bit farther, go through that ordinary system.
Yeah.
What do you think, Max?
I agree with everything you said.
Yes. Finally, my life is completed.
Yeah, I think that can pretty much wrap us up. I don't know, like usual, if you have any questions, reach out to us. We're trying to work on some audio issues over the last podcast, so we've got some new filters on here. And I've heard I should not laugh quite as much. Luckily, I've got a terribly sore throat, so I'm not laughing anyway.
Very true. We also have some very cool podcasts coming up.
Oh, yeah.
Collaborating with some people. And trying to bring you guys the most content, or rich content that we possibly can moving forward. We're currently working on actually a couple things here in our studio.
Yeah, that's right.
We got our wind tunnel. We're building a little wind tunnel.
And then a vibrating floor system demo.
Yeah, to go through a little bit of frequencies.
Damping and whatnot.
Damping and everything like that. So our YouTube, Instagram, Facebook, we're going to start posting videos and explaining things like that. Both of them we're still kind of working through, but once we kind of finish them, we'll put a build blog together on the website, and you guys can do it yourself, or we can, go from there. So
Sounds good to me.
super excited.
All right, guys. Thanks for listening.
You have a great day.